Hi, hello everyone. My name is Meriam Bautista. I'm a research intern at NERSC. I'm working with Thomas Davis, who's our environmental system architect engineer, together with Lisa, and Cary from the operations technology group. I'll be presenting today part of the research project that we're working on a scalable data warehouse for the operations monitoring and notification infrastructure at NERSC. So NERSC stands for National Energy Research Scientific Computing Center. It's a non-classified computational facility for the Department of Energy at Lawrence Berkeley National Laboratory. Its main mission is to provide computational resources to around 7,000 global science users with high availability of the HPC system. To support the management of the NERSC facility, the staff have instrumented the HPC floor with OMNI. OMNI stands for Operations Monitoring and Notification Infrastructure. It's a data collection system and warehouse that collects operational heterogeneous data at NERSC. That includes building management system data, sensor data, syslog data, cyberlog, and IODs. With the delivery of the new HPC system and because of the scale of the new machine, the data rate available is expected to be 100 to 1,000 times faster. Thus, it is anticipated that exascale size of data are to be sent to OMNI. As the facility is being prepared for the next system, reliability, scalability, and availability are essential requirements for OMNI. It also provides the team with a real-time, holistic view of the health of the data center and for further analysis to aid in business decision. To effectively manage the collection network and streamline this workflow, the NERSC operation team has developed an integrated network automation to scale OMNI's growth over the next few years. Back in 2012, the main issue the team encountered is that the monitoring and performance packages would not scale to the desired size needed for the HPC system. So the solution is to build and instrument everything monitoring infrastructure that is reliable, scalable, and easy to maintain. We started OMNI's network backbone upgrade last year in 2019. We rebuilt the network infrastructure to be scalable to meet the future demands for expansion. The team recognizes the importance of designing the infrastructure to be capable of ingesting new data and to scale dynamically to meet the demands for the exascale HPC. OMNI is implemented using an open source software and on-premise hardware and virtualization technologies. So operating a 24/7 HPC data center has unique challenges and requires careful orchestration of the system and to collect heterogeneous data sets from multiple sources. As an integral part of the building ecosystem, it is the first system to power on in the facility and the last system to power off in the building. The network infrastructure is implemented using a two-spine four-leaf topology. The management and data visualization is implemented using Overt and Rancher. We also use Elasticsearch and JSON for data ingestion and storage. Logs touched also to manage the component of the server, data processing, and Kibana for web interfaces. We also use Prometheus and Victoria metrics for scalable monitoring of the time series database and data compression, and Grafana for virtualization. The new backbone network adopted a scalable open networking solution and integrated automation strategy to accelerate the workflow. Software-defined networking approach enables us to efficiently manage the network architecture using software applications. At the SDN control layer, we integrated automation, routing, and monitoring. The network backbone design implements EVPN to leverage SDN-based networking solution and to support the end-to-end control plane for VXLAN and BGP for routing. The network automation is implemented using Ansible. We also use NetBacks for network virtualization and also serve as the source of truth. It allows us to map out the network topology, cable connections, and IP addresses. It also populates the monitoring and provisioning of the system. The new backbone network is already in production. This dashboard shows some of the critical values of the building management system that includes the cabinet air temperature, air supply, relative humidity, and the water supply temperature. This dashboard shows the time series monitoring data of the air handling unit and the wet and dry bulb. The AHU controls the humidity of the facility, and the wet and dry bulb indicates how much moisture is in the air. The moisture in the air reduces the air temperature and lowers the temperature of the building, thus less energy is being used by the AHU. They are inversely related. The higher relative humidity will decrease the temperature of the air handling unit. And this dashboard shows the time series average temperature of the sensor nodes at each rack of the NERSC supercomputer. The temperature data is collected using T-string temperature sensor mounted at the front and the back end of the cabinet doors. The temperature monitoring is critical to NERSC building management system. It is important that the temperature are within the nominal values. Thank you.